Okay, now I'm going to move on to the mesh. The mesh can be a little funny sometimes, so I'm going to do my best to explain it, but again, please refer to the AQWA manual. Um, it's a ton of help, and I think you can access that from here. Yeah, like the AQWA reference manual and theory manual. Those two are super, super helpful. But one thing to keep in mind is that the defeaturing tolerance has to be 60%. No, it can't exceed 60% of the maximum element size. And so basically what that means is if I were to make this 2, then ANSYS will yell at you. So you have to make this, see that doesn't even work. Let's 4 maybe. Okay, so usually what I do is come over here and then just hit generate just to see what the mesh looks like. Looks horrible, cool. So we'll go ahead and I'm gonna change this to that. Let's see how that looks. Okay, still pretty bad. So maybe 0.002. And now you can see that the maximum allowable frequency, I have in hertz right now, but I can change it to radians per second here. So now the maximum allowable frequency is 20.958 radians per second, and that's a lot. But basically, the smaller the maximum element size, the greater the maximum allowable frequency is. And so one of the requirements in WEXIM, I may state this a little backwards, but I'll post a link to an issue that I was having that the people at WEXIM were able to help me with. One of the things that you want to look for in your results, in your wave excitation and radiation damping specifically, is that the graph kind of goes up and then like tends towards 0 as the frequency approaches 0. And I'll explain that a little bit later, but one way you can do that is by increasing the maximum allowable frequency. So the smaller the mesh, the higher the allowable frequency is. However, the only downside is that AQWA has a limit. Its solver has a limit. And so the total number of elements can never exceed 18,000. Similarly, the number of diffracting elements cannot exceed 12,000, and that's stated in the reference manual or the theory manual, one of them. And so you can basically make this as fine as you want. This looks okay for our purposes. Again, it's highly recommended to do a mesh sensitivity study, which essentially is, you change this to 0.5 and make it super coarse. And then you run the analysis on it and then see what the results are. And then you'll change this to 0.1. Run the mesh, get all the information on it, and then plot those results. And then you change the mesh again, and you can do this, 3, 4, 5, 6 times, just to see if the results are sensitive to the mesh size. And so what you can do is you can figure out what is the optimum mesh size that gives me accurate results, but doesn't take a super long time to solve, because the denser the mesh, the finer these squares are, or these shapes are, the longer the simulation is going to take. So there's a trade-off between accuracy and simulation time. Right now, I'm going to make this a little bit more coarse, just for the sake of time, even though the results might not be super accurate, but just for the sake of time, I'm just going to keep it there. And at this point, we are done with meshing. And so now I'm going to move on to the hydrodynamic diffraction. So first, analysis settings. So there's a lot of these that you can change, you can keep the same. It really depends on just what you want. So parallel processing, I changed mine to manual definition. Again, like I mentioned earlier in a previous video, you can change the number of cores. Mine is 80, and so I'm not going to, I'm sorry, no it's not, my cores 40 cores. So you can change that to 40, and you should be okay, but I'm just going to keep mine program controlled for now. One thing that you do want to check, again, the AQWA manual gives a explanation of what all these things mean, so just go ahead and read that. One thing you will want to do, though, is to ignore modeling rule violations. Change that to yes, because there's going to be a bunch of really small errors that ANSYS will AQWA will pick up on, and then your simulation will fail. And so it's just better just change that to yes, and your simulation should run okay. Keep all these the way you want. For my case, for the wave energy converter, for what I was doing, I didn't need a QTF matrix, so I just turned that off. And I think if you turn on this, generate AHD pressure output, this is what's going to give you your output files. So that's going to give you your .ah1 file and your .lis file, which is what you'll need to use in WEXIM. So make sure that's on so you can get like a reading and like a whole list of your results, because you'll have your results here, but you'll need to have a way for MATLAB to read them. And so the AH1 and LIS files is the way to do that. I think on my simulations, I think I had potentials on as yes, but I'm going to leave them off for now. If you want an example database, it will override this. So if you want to just do a test simulation, you can turn that on and it'll tell you. I'll actually do that for now instead. I'm just going to have the example of the hydrodynamic database so I can run through what each of the values mean. And so now at this point, we're done with the analysis settings. Come down to structure settings. Since we only have one structure, it's just going to be structure ordering 1, it's just the flap. And then wave directions. So I'm only going to want three intermediate directions. And so what that's going to do is that's going to say, okay, we're going to analyze essentially the hydrodynamic coefficients, like those results from waves coming from this direction, which will be 0, from this direction, which I think is negative 180, from this direction, which is negative 90, and then this direction, which is 90. And so you can change that if you want. I usually just keep it there. And then let me go ahead and change this to degrees. Yeah. Okay, so 90-degree intervals, if you change it to 45, then you can see that there'd be 7 now. If I change that back to 3, okay, maybe not. So you can add waves, you can change them to a single wave, but you have to define like the speed of the wave. I'm not doing that. I'm just going to do these waves, so these different directions. And so next step is come on down to wave frequencies. So if you're going to be running it in WEXIM, you're going to want to have a large number of frequencies. So essentially, our maximum wave frequency in our mesh was 17. I'm just going to round that up to 20 just to make math easier. Let's just say this is 20 for now, the maximum allowable frequency. If we come down here, total number of frequencies, 20. That means we're going to have a wave frequency at 0.1, and then at 1, and then 2, and then 3, and then 4. But there's a lot of intermediate frequencies in there. And so we're going to want to make this pretty high. I think the maximum is 100, so I'm going to shoot for 80. And so now you can see that we have more intermediate frequencies. If I were to do, 10, then you skip a lot. And so there's a lot of wave frequencies that you're missing out on. So again, I think 100 is the maximum. And so you can see that you get a bunch of frequencies in between. So I'll just change this to, actually for this, to make it faster, I'm just going to change it to 50. And then you can also do like a manual definition of the range. So you can say the lowest frequency, I want it to be, and you can change it to period too. So longest period, let's say 17 seconds. And then shortest period, let's say it's a 2-second period. And so now you have these, and you can change the intermediate values. Let's say I want that to be 80. Then now I have a very fine change of wave frequencies. So I'm just going to do program controlled. I'm just going to do 50, but that's just another option for you. And now that we're done with setting everything up, I'm going to move forward to setting up the solution tab in another video.